Hi, and welcome to this lecture on systems design under the Systems Analysis and Design course. So far we have looked at the planning stage, where we said we do project planning as well as feasibility studies and project management issues, which deal with scheduling, resources, costs, etc. Then we moved to the analysis stage, where we looked at our requirements gathering, our requirements analysis, and our requirements analysis consisted of different types of diagrams that we can use, which include our context level diagrams, our data flow diagrams, as well as diagrams such as state diagrams, activity diagrams, and user case scenarios. And then we also looked at evaluating alternatives, where we're now looking at which softwares and which systems can we consider, which development methodologies, as well as the different hosting solutions can we actually consider for our solution. After that, we then now move to the systems design stage, where we want to actually see how our system works once it has been deployed. So with systems design, we're basically looking at how the system that we're developing is going to operate. Okay. So now we take those systems requirements that we came up with during our analysis stage, and we now want to translate them into a physical system that is actually delivering on the requirements and solutions that are required. So the activities that you find under the design stage are listed in this slide. So these are some of these activities. Firstly, I'm going to look at how are you going to get your system. Are you going to acquire it through outsourcing, insourcing, commercial off the shelf, and the like? So that's like looking at your alternatives to see how you do it. Then you look at your architecture design. You're now coming up with the architecture of your system, which we'll look at a bit later on. Then you also look at your hardware and software specifications, which we'll also look at later on. But under hardware and software specifications, basically you're looking at how much hardware in terms of RAM, storage, processing power is required. In terms of software, you're looking at things like what kind of programming language, what kind of middleware or platform does the software need to run on, as well as issues to do with portability and the like. Then you also look at the interface design. You design the interface that the users are going to interact with. Then you come up with a physical process model that actually translates that logical process model you developed under the data flow diagrams into a process model that's actually implementable using actual softwares and hardware. Then you also look at your case repository. You update it with all the system details that you are now going to use to develop the system. Then you also look at the various processes. As we did under the data flow diagram, you look at your various processes and you make sure that you have all the specifications of how you're going to actually get those processes to be implemented. Then as far as your data is concerned, you're now looking at how do I save and how do I manipulate the data that the system is going to require. Okay, so you will find that when it comes to data, you're now looking at how am I going to, which model am I going to use to develop my database? What kind of tables am I going to use? What kind of entity relationship diagrams am I going to come up with, so that you can come up with a proper way of doing it? Then you also look at your CRUD matrix, CRUD standing for create, retrieve, update, and delete. So you're looking at which transactions in your database are going to create data, retrieve data, update data, as well as delete data. Then you finally design how that data is going to be stored, on what kind of hardware, what kind of database, how is the data going to be accessed, and the like. Then finally, you come up with your system specification, and this system specification is what you then use to present to your sponsors, and which we are going to then use to implement the final solution under the implementation stage. So let's just look at the various things that you consider as you go through the design stage of a system. So one of the things that you have to consider is the input methods. How do users or how do other systems give data to this system that you're developing? So these are some examples of how people can input data: batch input, graphical user interface, remote batching, and all these other many examples. But the key thing that we just want to remember is that when you're dealing with inputting information, you want to make it as easy as possible for the user. So you look at things like just making sure that you capture only variable data. You don't force or you don't make the user capture data that the system can actually generate on its own. Okay, so there's no need for you to do that. And then you also need to have some controls as far as inputs are concerned. These controls will help you make sure that your program is containing accurate information, as well as you are providing risk management controls that help you and protect you against accidental or intentional errors, as well as crimes like fraud. So these internal controls will include completeness checks. This may look at, is the data that has been provided complete and accurate? Then you have limited range checks. So for example, if it's to do with edges, you may want people to input edges that are in a certain range. So if a person's edge is out of that range, they do not qualify. So you also need to see that your program is adhering to the limits and ranges that you need to work with. Then you also look at combination checks. So at times you may need a certain variable to match or to have to be in tandem with another variable. So for example, if a person is in part 1 and they have failed a certain course, then they should not be allowed to move to the next stage, which is probably year 2. So you're looking at now those combinations. For example, you could be using a decision table to do this. So you're looking at combination checks to make sure that the right combinations of information is available. So this is just a process on how you can actually come up with an input process, but it's quite simple really, and we'll cover this when we look at the user interface design topic. Then after you've come up with your input design, you also need to look at your output design. Now when it comes to outputs, it's very important that you also not overload the user with information that they don't need. So you only save them with the information that they require for that intended purpose, in the right quantity, at the right place, at the right time, and using the right method. So some of the methods that you could use for managing outputs is to understand the types of outputs. For example, internal outputs are outputs that stay within the system, okay? And these are used by the users and managers, like reports, whether they are detailed or not, and the like. Then external outputs are these that leave the system, and these may leave as a result, as probably something that's printed, or it's sent to another system that's been integrated with this system. And when these inputs are sent out, these outputs are sent out, then they are used differently from the system. So you need to understand this type so that you know how you are dealing with your outputs. If it's outputs that are just going to stay in the system, then there's no need for you to put up a lot of printing and a lot of emailing for those outputs. At the same time, if they are external outputs, they may be need for you to view them within the system, but at times it may be just better to email them depending on the amount of resources that you have, or to print them if that's the requirement that you have. So these are types of internal inputs, which are basically more to do with reports, detailed reports, or exception reports, as well as summary reports. And then here we're now looking at the principles that and guidelines for output design. So these are the things that you need to consider as you come up with an output. For example, the selection of an appropriate medium and format for an output depends on how the output will be used and when it is needed. So you are going to have to look at the context in which the various data or outputs of the system are going to be used, and then you develop a proper solution for that context. So this is still discussing principles and guidelines for output design, so that you know how to output your information and which medium do you have. So at the end of the day, we have got various output media, output formats, and you need to always consider this. But I think the most important thing is to remember these output guidelines. For example, every report or output screen should have a title. Legends should also be used formally to define all fields on a report. You never know whose hands the report might end up in. So that's basically speaking to clarity, to say whatever information you are inputting or whatever information you are relating, it has to be clear for whoever is going to get that information to know the meaning of that input. Okay, so now let's also look briefly at output design. So when you're designing your outputs as well, be aware of output design, output bias. Also, the timing of your computer outputs is important. So your outputs at times need to be immediate, or at times they need to be delayed a bit. So you also need to be careful about that. The computer outputs must also be acceptable to the system users who receive them. So when you give out an output, it should be in a format and in a manner that the user will be happy with, to be able to use that. So this is also another way of coming up with an output design. We can follow that as well, because it basically follows the prototyping type of structure. So we've so far looked at input design and output design. Now let's look at our file and database design. So when you're looking at your database and file design, you've got various stages at which you design it. So you've got the conceptual level, the logical level, and the physical data level. So the conceptual level, you're probably looking at the various modules that you can use. The logical level, you're now implementing those modules, for example, our entity relationship diagram. And then the physical level, that's where we're actually looking at how we're going to store the information in our database and how we're actually going to manipulate it. So when you select your data model, one of the most common one at the moment is the relational data model. So you can select that one and use it for your database. Then you will use entity relationship diagrams to be able to show the connection between the various entities or the various tables or the various data that you have and how you're going to store it in the database. Then you need to normalize your tables so that you have information that meets the ACID properties of atomicity, consistency, integrity, and durability, so that your data is never in a state that gets it to be compromised in one way or the other. After you have that, you can also come up with a data dictionary to explain all your information as well as metadata. Then when it comes to the actual database, the physical database that you're going to look at to implement, you now look at resource allocation. How much compute, memory, and storage do you require? How much hardware do you require? And then do you need to store all the tables normalized, or you need to denormalize some of them? Do you also need to index some information for quick searches of your database, as well as what information needs to be stored and what information needs to be calculated at runtime? So as we said before, at times do not ask the user to give you information that the system can calculate on the go. At the same time, do not store information in your database that can be calculated on the fly, so that you avoid creating unnecessary data overload. Then after that, you also need to consider your database architecture. Are you going to use a distributed database where you will have either 2 or more copies of the same database in different locations, or you are going to use some sort of segmentation where you have some tables in a different location? For example, customer tables will be in Harare because that's where your shops are, but your accounting tables will be stored in Bulawayo because that's where your headquarters is. So that could be some form of horizontal segmentation. Or you could actually have certain columns being stored in different locations. So those are different database architectures that you can consider. Are you going to have a standalone database, which is just one database sitting in one place and doing everything on that database? And then you just make sure you've got some level of redundancy or backups for that. Now, some of the things you need to consider as you deal with your data and as you come up with your data policies as well as your architectures is, how do you deal with user identification, user password and privacy? How do you allocate permissions? Is it user-based or is it role-based? How do you encrypt and make sure that your data is not visible in plain text to anyone who wants to see it? How do you back up your data, and how do you restore it in the event of some data corruption or data loss? How do you recover from a database crash or some data loss, as well as how do you audit that information? So you need to consider all these things when you're coming up with a database architecture, as well as the various solutions that you're going to use to come up with the system. Now, so we have looked at input design, output design, database design. Now let's look at system architecture design. So you'll find that with the system architecture design, probably this is the most important part, because it puts together everything and allows all the other things that we've been looking at, the inputs, the outputs, the database, to be able to function as one unit. So we'll look at some of the architectures that are available out there. So when we are looking at system architectures, a very key factor to remember is that we are looking at our non-functional requirements. Okay, so during the analysis stage, we would have hoped that you would have come up with your functional and non-functional requirements. And remember, non-functional requirements are the requirements on how, on basically what the system needs to be able to function. So functional requirements are what the system does. Non-functional requirements are how the system works. Okay? So, for example, you may want your system to process 1,000 transactions per second. You may want your system to give outputs within 1 second. You may want your system to have a certain level of security. Now, those things do not affect the actual functions of the system, but they help make the system function better, as well as protect your data and your users. So these things now will come defined in your non-functional requirements, and then you translate them into hardware and software specifications that will fulfill these non-functional requirements. So the architectural components that we need to consider when you're coming up with with a system architecture are mainly 4. Number 1 is, how are you going to store your data? So there's the issue of data storage. Number 2, there's the data access logic. How do you access the data that is stored somewhere? Then there's the application logic. How does the application manage the various business rules, the various data flows, as well as the use cases? And then there's the presentation logic. What do you display to a user, as well as how do you display it? So we'll look at these 4 components in the next few slides. So in our architecture, we have 3 main components as far as hardware is concerned. We have the client computer, that is your PC or your Mac. Then you have your servers. So your servers are basically giving information out to those who require it. And then you have got the network that connects your servers and your client computers. Now, given that we are talking of servers being connected to clients through a network, we have what is called a client-server architecture. So with a client-server architecture, basically we have a client device, or we have a PC that is used by a user who is trying to access information that is stored in a server. So a server is basically a computer that's serving information to a user who requires that information. So the user is called the client, and this computer that's serving the data is called the server. So that's where the client-server architecture comes from. Now, when we are doing this client-server architecture, we will see that there are various tiers to client-server architectures. Some have got many tiers, some have got very short tiers, and we'll look at them briefly. But what I want you to note at the moment is that there are different types of clients out there. You could have a thick client or a thin client. So you'll find that a thick client is one that contains most of your application logic. So basically, all the computations are done on your computer, on your own PC, and not on the server. And then a thin client is one where only the presentation is available on your PC. So your PC is only showing you your information. For example, when you're dealing with a Facebook page, your PC does not do any computation. All it does is show you your Facebook page. But when you're dealing with an Excel spreadsheet, most of the computation is done on your computer, and maybe some data now may be extracted from a MySQL database that is being stored somewhere. So when you're dealing with Excel, your computer is a thick client, but when you're dealing with Facebook, your computer is a thin client. So why is client-server architectures one of the favorite ways of deploying your systems? The first reason is because these are scalable. So when you look at the various tiers, you can add as many systems as you want and various stages as you want to your architecture. They also allow you to have different middleware and to have different types of clients and servers which you connect using this middleware. Then they allow you to separate the presentation, application logics, as well as the data processing and the data presentation layers, or in the data storage as well. And also, if a server fails, you can actually have 2 or more servers doing the same work. So if one server fails, the other ones can kick in. And if one server fails, it's only the applications running on that server that are affected, and the rest of the servers will continue working. So it makes it easy for troubleshooting. It makes it easy for quick recovery from problems, because you're able to quickly get the solutions going. And then a limitation of client-server architecture is their complexity, but I would like to say, as far as the complexity is concerned, that is actually based on how you deploy a system. Because in some instances, or you'll find that client-server architectures are actually very simple if you deploy them very well in a very simplistic way. But if you also have very complicated systems, you may end up having so many integrations that make it difficult for you to follow or to know what exactly you're doing. So let's look at the various client-server tiers. So we have a two-tiered application or a two-tiered client-server architecture. So this one has got a client device connecting directly to a server. Now this server handles the data access as well as data storage. So basically the server is like a database server that is storing your data, and the client does all the processing on itself. So this is the case where, for example, I was saying your Excel could be doing all the presentation and application logic on your PC. But if you need some extra data, you can integrate your Excel with data that is coming from a server. So that becomes a two-tiered architecture, and that data is coming from a server and is being used on your computer, but your computer is the one doing all the computation. So that makes your computer a thick client that is getting data from a server. Then we have a three-tiered architecture. Now with a three-tiered architecture, we are now taking away the application logic from the client, and we are creating a dedicated server just for handling application logic, and that is the application server. Then we also have a database server that contains your data storage as well as your data access logic. So with the three-tiered architecture, as you can see, you have a client device that connects to the application server, which handles the application logic. Now based on the logic that is being required, the application server then queries the database server to access or retrieve the information required, which is then sent back to the application server and back to the client device. So a three-tiered architecture is basically 3 stages, and that's how they work. So these stages can actually increase from 3 to 4 to 5 to 10 to 20, depending on how you want to separate your various applications, and also depending on the various components that you're integrating. So you could have an n-tiered architecture, which could have as many stages as are required. So in this instance, you could actually further separate your application server into a web server. You could actually further separate your database server into one that has got data storage and one that handles data access logic. So with an n-tiered architecture, you can have so many servers doing different functions but connected together using a network. So this is another less common architecture, but which I think these days might actually end up being popular. So we've got a terminal, which is basically a screen which does absolutely nothing but just display information. And then you have a server now that does everything. So for example, if you look at cloud computing these days, if you create a server, what your computer is just doing is showing you what is happening. It's acting as a terminal. But all the processing, all the presentation logic, all the application logic, and all the data storage is being stored in the cloud, in AWS, in Azure, or in our Liquid Telecom cloud infrastructure. So just remember that this can also be used for desktop virtualization. For example, if you want your users to be able to store their information to do it work on your server, you may actually just give them a client which they use to access that server, and all the softwares and their data that they have stored are stored on a server, such that if the terminal or if the computer that you have that you gave them is stolen, they can still access the information, because that computer is just acting as a terminal. It stores nothing whatsoever, but it's just an interface, whereas everything else is on the server. And then this one again is more like a thick client and a server, and they're connected together in a two-tiered architecture. So we've also looked at our n-tier, our client-server architecture and the various tiers that we can have. Now, we also need to know how we are going to deploy the system. Okay, so these days, some of the most common ways of deploying our systems are through virtualization, as well as cloud computing, or a combination of both. So virtualization basically is taking some hardware resources and partitioning them such that you can deploy different applications or different operating systems on that hardware, and those different operating systems will act as if they are sitting on their own hardware, even though they are sharing the same hardware. So virtualization is like dividing a room into many rooms, but the people who live in those rooms act as if they are the only ones living in that house. They don't even know that there are other people there. But even if they do know that there are other people there, there's just probably a corridor where you share access into the house or out of the house. But once you get into your rooms, no one knows what's in there. You act as if you're the only person in the house, and that's what virtualization is basically like. So virtualization can occur at server level, where you're partitioning hardware to be able to function, to run different operating systems, or it can also happen at storage level, where you can actually take different disks and then you combine them logically to appear as if it's just one disk. So for example, you could buy 10 disks, and all those disks, they've got storage of 1 TB each, and then you combine them using some storage virtualization application, such that when you present that storage to the computer will only see 10 terabytes, but it will not know that these are 10 1 TB disks that have been combined. So as far as this computer is concerned, it is working with TB. It does not care about how, with 10 TB, it does not care about how the information is being stored at the hardware and how the hardware is organized. That's the responsibility of the virtualization software for storage. So that's another way of virtualizing. Then cloud computing, I think we are in the era of cloud computing, where your applications run on a rented server that is hosted somewhere else by someone else, and you focus on the level that you want. So you could actually you could just use infrastructure as a service, where you want the hardware but you don't want to buy it, so you're just renting. You could use software as a service, where you just want the software but you do not want the problems of installing it and buying hardware and the like. You could use platform as a service, middleware as a service. There are different types of cloud computing services that you can use to be able to deploy your application. So you can actually consider those as you design your system and as you deploy the various things. So when it comes to your architectures, you need to be able to know the advantages and disadvantages of each architecture. You need to be able to know why it's better for you to have an on-prem deployment compared to a cloud deployment. Why it's actually better for you to in-source the development of a system versus outsourcing it. Why it's actually better for you to use an Oracle database compared to a MySQL database. So you need to be able to compare those things and come up with a good justification that allows you to do all those things. So you can look at these things based on things such as cost of deployment, technologies that are being used, technical complexity of the solutions, as well as probably future proofing of the systems. For example, are the systems compatible with either legacy or future systems, and are the systems going to be around for a long time, such that all you need is to update it, or you need to purchase a brand new system after every couple of months or years. So when you're looking at when you're creating your architecture design now, as I said before, you need to look at your non-functional requirements. And these non-functional requirements are the ones you're going to use to develop your hardware and software specifications. So some of your non-functional requirements can include operational requirements that have to do with things like your integration requirements, portability requirements, maintainability requirements, as well as your technical environment. You also need to look at your performance requirements. What's the speed of your system that's required? What is the capacity? How much storage does it require? Or how much can it store at one single time? As well as your uptimes. What is the availability as well as reliability of your system? Is it going to be up 24/7? Is it going to have 99% uptime? If it goes down, how long can it go down before it comes up? Does it come up automatically, or do you need somebody else to bring it up? Then you also look at your security requirements. For example, access control, encryption and authentication, virus controls, etc. Those are things that you need now to consider, so that even though your system can do all the functions, if a hacker gets into the system, you will not be able to use it anymore, or your information will be compromised. So it's important that you understand and you also implement these non-functional requirements. And then you look at different things that have to do with your political, economic, social, and technological issues, such as cultural and political requirements. And then you can come up with a matrix that helps you to look at how do I then implement these things? Do I have these things? Do I require these things? And this table is showing you which kind of architecture meets those kind of needs. And you can see that a thin client or server architecture meets most of those needs and is probably the best to use. So yes, I would also recommend a thin client to a server kind of architecture. So basically, this is what you need to consider. So you have looked at all your various requirements, and now you're coming up with your hardware specifications and your software specifications. So based on the application that you want, you could say, my web server is going to run a Linux server. It's going to need an Apache software. I'll need 500 gigabytes of disk with a dual-core Xeon processor, and I'll need 100 megabit per second Ethernet link to be able to run my web server. If I want for my database server, I also want a Linux server, but I want to be running an Oracle database, and I want a 1 TB disk drive, which has got a RAID configuration there, and then the processor should be a quad-core Xeon processor, and the network I should have 100 megabit per second dual Ethernet link. So these are the kind of hardware and software specifications that you end up with, such that when it comes to the deployment of the system, you present this to your engineers, and then they make sure that they deploy this as required, and then the various application developers and integrators will then come in and work on integrating all the information so that it works well. So basically, these are the issues that you need to consider when you're coming up with your systems design. This stage is not cast in stone to say you're going to do this or do that, but these are basically the main stages or the main things that you're definitely going to do if you're going to do this stage right. So you can actually tweak it to suit your environment, to suit your market, to suit your operating environment, and to suit your regulatory requirements, as well as to suit your budgets. But basically, if you look at all these things as you come up with your plan, it will help you to improve your operations and to come up with a system design that is feasible and that is efficient. So thank you very much for listening. I hope you have a good day.